Okay, so today, welcome. Today we're going to learn about second order, linear, non-homogeneous differential equations with constant coefficients. Okay, so unraveling all of this, let's see here. We can figure out exactly what the differential equation is going to look like. So if it's second order and it's linear, we know it has to look like something like y double prime plus p of x y prime plus q of x y equals f of x. Okay, if it's non-homogeneous, then we know that the f of x, this is not the zero function. And then lastly, if we're told that we're going to have constant coefficients, that means that p and q are constant functions. So these are constant functions. So that means that our function is going to look something. We're going to be solving differential equations that look kind of like, a y double prime plus b y prime plus c y equals f of x, where f of x is not the zero function. Okay. So I want to start off with a theorem, and this is tying into the theorem that we had in the big theorem that we had at the end of class on Thursday. And we're saying that if you have a function, now I'm just going to, so you can look here and you can see this is the general format, right? So y double prime plus a y prime plus by equals f of x. Now, all I need to do is, before we were writing it with the little f, and now we're just writing it with the big F. It's the same thing. We're just talking about a function. And of course, our a and our b are constants, right? So here, a and b are constants. Okay, so it says, let this be a second order non-homogeneous, wait, did I put non-homogeneous? Yeah, non-homogeneous linear differential equation with constant coefficients. Now, if yp is a particular solution of our differential equation here that we're trying to solve, and YH is the general solution of the homogeneous version, okay, then here is our general formula, y equals yp plus yh. That's the general solution of our differential equation. So let me write that down. So yp stands for the particular solution. Oh, it's already written here. So that means yp is any specific solution of this differential equation. YH is a solution of, is the general solution of the homogeneous version of our differential equation. Then to get the general solution of our non-homogeneous version, we just need to add together yp plus yh. Okay. So notice that yh is going to have constants, c1 and c2, two constants, right? Yp, on the other hand, we're not sure what it'll be. We know that we can always find YH because we know that there are only three different scenarios. We know how to solve this homogeneous equation because you form your auxiliary equations. So it'd be r squared plus a plus ar plus b equals 0. And then you see what are your solutions, solve for r, r1, and r2. And then based on r1 and r2, you can figure out the general solution, right? So we'll always be able to find YH. The key is finding YP. Now here's our method. Our method that we're going to use is the method of variation of parameters. Here's what the method consists of: 5 parts. So step 1 is to find your YH by solving the homogeneous differential equation. Okay. Step 2 is you're going to let YH equal C y1 plus cy2, right? We know that that's the general form of a solution to this homogeneous equation. So you're going to replace c1 and c2 by u1 and u2, okay? That is how you're going to form your YP. So that's how we get that's why the method is actually called variation of parameters. What you're doing is you're going to let your coefficients vary, right? So you're letting C vary, and instead of C being just a constant, you're going to say, what if C changes, i.e. what if C is a function? So that's how we get this U1. And the same thing with our constant our constant for C, our second constant will allow it to vary. So we are allowing our parameters to vary. And that's how we get variation of parameters, right? So we're letting these parameters, C1 and C2, vary, and then we're solving for those functions. So I want to point out here how this is very similar to what we had when we just had a first order linear differential equation. We had our solution y1, and then we made the assumption that y is equal to u1 y1, right? And then we found out that if y1 solves the homogeneous version of the differential equation, then does this sound familiar? So we said if y1 solved the homogeneous version of the first order linear differential equation, then we came up with an equation that u1 had to solve, right? And then that's how we figured out the general solution to the non-homogeneous version, okay? Non-homogeneous first order linear differential equation. We're going to be doing that same exact thing, except for here we'll have yp equals u1 y1 plus u2 y2. So in the case of the first order differential equations, the formula we had for u1 was u1 prime is equal to, I think it was the f, or it was the q actually, I think we were using q of x over y1 of x. Do you remember? So then in order to find u1, you just needed to integrate. Well, here we've got to solve for u1 and u2. So we have two equations, and we'll be solving for two functions. And these are the equations that we'll be solving. And so I'm not going to get into, maybe I'll post a video later on explaining how we derive these equations. But for right now, I want this video to focus on just applying this method. Okay, so step 3 is going to be to solve the system. Step 4 is going to be able to, so when you solve the system, you're going to solve it for u1 prime and u2 prime. So you'll have u1 prime equals, some function of x, u2 prime equals some function of x. Okay, step 4 is to integrate your equations, right? Integrate to find u1 prime, to find u1 and u2. And then the last thing you do is you put it all together and you say, therefore, y is equal to yh plus yp, where yh is going to be from here and yp is going to be from here. Okay, so this is more complicated, and again, that's why we learned solving first order equations with the method of variation of parameters, so that now that you're seeing this method, you're not as freaked out, because some parts of it look very familiar. Okay, so let's go ahead and do some examples. The first is we're going to solve this differential equation. So here we've got, so this is our constant here. So here's a, well actually this is the differential equation, is right here. And we've got our domain for it. Okay, so we've got our function here, f of x. And we know that a is equal to -2. And, well, we'll see. We'll see. Let's go ahead and just get started. Let's jump into it. So this is what we're trying to solve. So let's go back to our steps. So hopefully, excuse me. Let me go here and let me pause. So now what you should be doing as you're watching these videos, you should be taking notes just like if you were in class. Okay, so you should have these steps written down because you were taking notes with the video. Okay, so I pause it here, pause it, take notes, Okay, now let's see here. So we're going to do step 1. And step 1 is going to be we need to solve the homogeneous version of this differential equation. So we need to solve y double prime minus 2y prime plus y equals 0. Okay. So now how are we going to do that? Well, I'm going to form my auxiliary equation. So I'll have r squared minus 2r plus 1 equals 0. And from here we should get, I think I can factor this, it's just r minus 1 squared equals 0. So I'm in the case where I have r1 is equal to r2 is equal to 1. So I've got repeated roots and they're real. So my general solution is, my solution to, let's call this star, or we'll call this one star, and we'll call this one double star. So double star is just the homogeneous version of star. So my solution to double star, the general solution, is, let's see here, so it'll be, so this is my homogeneous general solution, YH equals C1 e to the x plus C2 x e to the x. So remember, it's supposed to be C1 e to the R1x plus C2 x e to the R2x equals y. That's the general solution. Okay, so for us, since R1 and R2 are equal to 1, our coefficients are just e to the x. Our exponents are just e to the x. Okay. All right, so we've got this. That's good. That's the result of step 1. Okay, now let's do step 2. Step 2 is we're supposed to figure out y1 and y2. Okay, so since YH is equal to C1 y1 plus C2 y2, okay, and that's also equal to C1 e to the x plus C2 x e to the x. So y1 must be e to the x, and y2 is equal to x e to the x. So can you see here? So if we've got this C1,
it's 1930.
Thank you. C1 y1 is C1 e to the x, so that means that y1 is equal to x, and C2 y2 is equal to C2 x e to the x, so y2 is x e to the x. Okay, so we figured out y1 and y2. Now we need to replace the constants with, right, we need to vary our parameters. So we need to form yp is going to be u1 y1 plus u2 y2. Okay, and so we can write this as, in fact, which is equal to yp equals u1, and y1 is e to the x, u2 y2, which is x e to the x. Okay, so now let's go to step 3. Step 3 is we need to solve the system for u1 prime and u2 prime. And what are we going to solve? Here's our system. Our system is u1 prime y1 plus u2 prime y2 equals 0, and u1 prime y1 prime plus u2 prime y2 prime equals f of x. Now, what is our f of x? Our f of x is going to be right here. It's going to be e to the x over 2x. Okay, so we can replace this with e to the x over 2x. Okay, and now we need to figure out what is y. We know y1, so we can go ahead and replace y1 because y1 is e to the x. So we'll have e to the x. y2 is x e to the x. X e to the x. Okay, so now if y1 is e to the x, what is y1 prime? Y1 prime is just going to be e to the x. And y2 is x e to the x, so y2 prime is equal to, now we need the derivative of x e to the x. So we need x e to the x prime, and that is we're going to use the product rule, so we'll get e to the x plus x e to the x. We can rewrite this as just 1 plus x times e to the x. Okay, so I'm going to replace y1 prime with e to the x, and I'm going to replace y2 prime with 1 plus x e to the x. Now I have my system that I'm ready to solve. So my system is, so I've got u1 prime e to the x plus u2 prime x e to the x equals 0, and u1 prime e to the x plus u2 prime 1 plus x e to the x equals e to the x over 2x. Now, in the first equation here, I can factor out an e to the x because we have an e to the x, and in fact in the second equation I can also factor out an e to the x. So we'll have e to the x times u1 prime plus u2 prime x equals 0, and then for my second equation I'll have e to the x times u1 prime plus u2 prime times 1 plus x is equal to e to the x over 2x. Now, from here, notice that if this function times this function is equal to 0, e to the x is never equal to 0. So I can multiply both sides by e to the negative x, and we'll see that if I multiply both sides by e to the negative x, and I can do the same thing down here, right? Multiply both sides by e to the negative x. Things are going to cancel out. I can rewrite my equation as u1 prime plus u2 prime times x equals 0. And for the second one here, I'll have u1 prime plus u2 prime times 1 plus x equals 1 over 2x. Okay? Now, if I distribute the bottom, the second equation, I'll see that really what I have is u1 prime plus u2 prime x equals 0, and u1 prime plus u2 prime plus u2 prime x equals 1 over 2x. From here, I know that u1 prime plus u2 prime x is equal to 0, so this u2 prime x plus u1 prime, that has to be equal to 0. Okay, so this tells me that u2 prime is equal to 1 over 2x. So u2 prime is equal to 1 over 2x, right? Because that's the only thing that's left, right? So I've got the u2 prime, and I've got 1 over 2x. So I've solved for u2 prime. I'm done here. Once I have u2 prime, I'm supposed to solve for, I need to figure out u1 prime. Because remember, I'm supposed to solve the system for u1 prime and u2 prime. And so far, I've figured out that u2 prime is equal to 1 over 2x. Now I've got to find out what is u1 prime. And in order to do that, I can go back to this equation up here, this first equation here. So if I know u2 prime is equal to 1 over 2x, so then I can substitute 1 over 2x for u2 prime, multiply that by x, and I get something equal to 0. So now u1 prime plus 1/2 is equal to 0. So u1 prime is equal to negative 1/2. So I have now solved for u1 prime. It is negative 1/2. Now I'm smiling because at this point step 4 is easy. In step 4 I'm supposed to integrate to find u1 and u2. And so now I know that u2 prime is equal to 1 over 2x. So if u2 prime is equal to 1 over 2x, then u2 is going to be the integral of 1 over 2x dx. And that is just going to be 1/2 natural log of x. Okay? And u1 prime is equal to negative 1/2. So u1 is equal to the integral of negative 1/2 dx. So that's going to be negative x over 2. So I've got that. And now step 5 is the fun part. So for step 5, what do? We combine it all. And so we say so let's say put it all together. And what is the it? Well, now remember, y is supposed to be equal to yp plus yh. So y is equal to our particular solution plus our solution to the homogeneous equation. And now what is yp? Well, yh, we found that out from before. Yh was c1. What was yh? c1 e to the x plus c2 x e to the x. And yp was u1 u1 y1 plus u2 y2. But now we figured out that u1 is 1/2 natural log of x. y1 is e to the x. u2 is negative x over 2. y2 is x e to the x. Okay, so when we put it all together, y is equal to e to the x natural log of x over 2 minus x squared e to the x over 2 plus c1 e to the x plus c2 x e to the x. Okay, and we can simplify this a little bit by pulling out the e to the x, right? So we could have the e to the x times natural log of x over 2, c1 plus natural log of x over 2, plus c2x minus x squared over 2. And that is our final answer for the general solution. Okay, let's do another problem. We want to solve this differential equation. Y double prime plus y equals tangent of x. And this is going to be over the interval pi over 2 to pi over 2. All right, let's do it. So step 1 is going to be to solve we need to find YH. Okay, and so now to find YH, we're going to form our characteristic equation, which is going to be r squared plus 1 equals 0. So that means r squared equals -1. So r equals plus and minus I. Now, we're supposed to take r and write it as alpha plus or minus beta I. So in this case, alpha is equal to 0. And beta is equal to 1. Because we can write this plus or minus I, we can write that as 0 plus or minus 1 times I. So now we know our alpha and our beta. Because our YH is equal to e to the alpha x times C1 cosine beta x plus C2 sine beta x. Okay, and now alpha is 0, so we'll have YH equals e to the 0 times x times C1, and beta is 1, so it'll be cosine of 1 times x plus C2 sine of 1 times x. And that's just C1 cosine x plus C2 sine x. Okay? So, we found YH. And step 2 is going to be we're supposed to figure out y1 and y2. So step 2, let's see here, step 2. YH is equal to C1 y1 plus C2 y2. Okay, so y1 is equal to cosine of x, and y2 is equal to sine of x. Okay, we're supposed to replace the constants with variables, so this is where we vary our parameters. Now we're going to say yp is equal to u1 y1 plus u2 y2.
It's 1945.
Thank you. Okay. And we can move on to step 3. Step 3 is to solve the system of equations, and our system is going to be u1 prime y1 plus u2 prime y2 equals 0. u1 prime y1 prime plus u2 prime y2 prime equals f of x. Okay, and so for us, we know y1, we've already said y1 is going to be equal to cosine x, y2 is going to be sine x, and now what is our f of x? F of x is the forcing term, so that's going to be tangent of x. So f of x is tan x. And now y1 is cosine, so y1 prime is going to be negative sine x. y2 is sine, so y2 prime is going to be cosine x. And I believe we are ready for our system. So we need to solve u1 prime times y. U1, which is cosine x, plus U2, need to solve this for U1 prime and U2 prime, plus U2 prime sine x equals 0, and then U1 prime negative U1 prime sine x plus U2 prime cosine x equals tan x. So this is our system. So now, in order to solve this system, what I'm going to do is I'm actually going to, let's see here. If I multiply this top equation by, I can multiply the top equation by sine x, and then multiply the bottom equation by cosine x. Right, then I should have some things cancel out. Because, for instance, I'll have cosine x sine x u1 prime, and here I'll have minus u1 prime sine x cosine x. So I can add the resulting equations, and I should have the resulting equation should be just in terms of u2 prime. All right, so good plan. Let's go for it. Okay, so I'm multiplying the first equation by sine x, so I've got u1 prime cosine x sine x plus u2 prime sine x squared equals 0. And the second equation I'm going to multiply by cosine x. So I have minus u1 prime cosine x sine x plus u2 prime cosine squared x equals, now what is tan x times cosine x? Tangent is sine over cosine, right? So it'll be sine x over cosine x, but I'm multiplying it by cosine x, so I'm actually left with just sine x. Okay, so equals sine x. And now I'm going to add the equations, and when I add them together, this plus this is going to be equal to 0, so they cancel each other out. And then here, I'll actually get u prime, u2 prime, because sine squared plus cosine squared is equal to 1, right? And then over here, I'll get sine x. So it looks like u2 prime is equal to sine x. So then, so we found u2 prime. So we've got u2 prime. Now I just need to find u1 prime. So we can go back to our first equation. If we know u2 prime is sine x, so we can just replace, for instance, here, replace u2 prime with sine x. Okay, so then u1 prime, let me go over here. So u1 prime cosine x plus sine squared x is equal to 0. Negative sine squared x is equal to u1 prime cosine x. And u1 prime is equal to negative sine squared x over cosine x. So we've solved for u1 prime as well. Now we are ready, I believe, for step 4. So we need to integrate to solve for u1 and u2. So now what is my u1? Okay, so I think the easier one is u2 prime, because u1 prime is going to be negative sine squared x over cosine x, and u2 prime is going to be sine x. So easy is to just say u2 is going to be the integral of sine x dx, which is negative cosine x. Okay, notice that for my particular solution, because it's a particular solution, if I say plus a constant, I choose my constant to be equal to 0, right? So the u is a particular solution. The YH is going to have your arbitrary constants. Okay. Now let's see if we can integrate this to figure out u1. u1 is going to be equal to the integral of sine squared x over cosine x dx. And now the key here is to notice that sine squared x over cosine x is really sine squared x over cosine x is really equal to, let's see here. Let me see. So we've got a couple of options. I'm going to go to the side. So sine squared x over cosine x. On the one hand, we could write it as negative sine x over cosine x times sine x, right? Which would give us negative tan x sine x. But we remember from calculus 2 that tangent and secant go well together. Tangent and sine don't go well together. Tangent and secant go well together. Sine and cosine go well together. And cotangent and cosecant. So, instead of rewriting u1 prime like this, let's recognize that sine squared is equal to 1 minus cosine squared. Okay, so we've got this over cosine x. Now we've got negative 1 over cosine x plus cosine x. And this we can rewrite as negative secant x plus cosine x. Okay, so this is u1 prime, and because tangent and sine don't really work out well together, we said let's not use this. Even though that's true, it's not going to be helpful for integration purposes. What would be more helpful would be to use the fact that sine squared theta plus cosine squared theta equals 1. So that means sine squared theta is equal to 1 minus cosine squared theta. And so I just replaced sine squared theta, sine squared x, with 1 minus cosine squared x in the numerator. Okay. And then once I did that, I was able to break it apart and have, this is secant, right, negative secant x, and this is cosine x. Because I know how to integrate secant x, cosine x dx. The integral of secant x is, let's see here, yeah. Remember there's that old trick for the integral of secant x dx? The key to integrating secant x dx is to multiply by, what is it, secant plus tan, secant x plus tan x in the top and in the denominator. And then what we have is the integral of secant squared x plus secant x tan x in the numerator and secant x plus tan x in the denominator. And we can do a u substitution, right? So let u equal secant x plus tan x. Then du is going to be secant tan plus secant squared. And all of that dx, right? So our integral over here is going to be equal to the integral of 1 over u du, which is going to be natural log of u. Back substitute to get natural log of secant x plus tan x. Okay, so over here, I'm trying to solve for u1 prime. I'm trying to solve for u1. We've got all this extraneous matter here. The bottom line is that u1 is going to be equal to negative integral secant x dx plus the integral of cosine x dx. And the integral of secant x is natural log secant x plus tan x. So we'll put our negative in here. And then the integral of cosine x is just secant x. Okay, and again, I could say plus c, but I'm just going to let c equal 0. Right? So there's no point in even writing it because I'm looking for a particular solution. So I've got u2 is negative cosine x, and u1 is secant x minus natural log of secant x plus tan x. And now that I have u1 and u2, therefore, my y particular, which was u1 y1 plus u2 y2, is going to be, what's y1? Let's see here. Y1 is cosine x. Hold on right quick. No, I'm good. It's fine, whatever you want to do. Okay, all right. No problem. Good night. Have a good weekend. Okay. So, sorry about that. So we said y1 was equal to, here we go, y1 of x, and y2 is sine of x. Okay, so we will have cosine of x. So y1 is cosine of x, and y2 is sine of x. So now let's put this all together to get yp. So we need u1, y1. So it'll be u1, y1 is going to be secant x minus the natural log of secant x plus tan x times cosine x, okay, plus u2, y2. u2 is sine x and y2 is negative cosine x. So let's actually write minus sine x cosine x. Okay. Let's see here. So we'll have secant x cosine x minus the natural log. Let me put the cosine x first. Minus cosine x times the natural log of secant x plus tan x. Okay, and then all of this minus sine x cosine x. Now secant x cosine x we can simplify because secant of x is 1 over cosine of x. So we actually will have 1 minus cosine x times the natural log of secant x plus tan x. And all this minus sine x.
It's 20 hours.
Cosine x. Thank you. Okay, so this is the yp. Okay, and then now step 5 is to put it together and to say, I would like to just, so step 5, put it all together. To get our general solution, which is y equals yh plus yp. Okay, so now y is going to equal yh. What was yh? Yh is c1 cosine x plus c2 sine x. c1 cosine x plus c2 sine x. Okay, and then, so that was yh, and now yp is this part right here, plus 1 minus cosine x natural log secant x plus tan x, and then minus sine x cosine x. And so that is our final answer. I know it's so small you can barely see it, but there you go. Okay. And now what I wanted to do is I just wanted to give just a little bit more practice with actually solving the system of solving the system of equations, because this is the trickiest part of it. The key is, how do you know how to solve this system, right? We're used to solving systems when it's just variables. I mean, when it's constants, but we're not really used to solving systems, and we're solving it for a function, or two functions actually. So let's look at this last example here. So we want to solve this system here. Our goal is to solve this system. Ooh, sorry. We want to solve the goal is to solve the system for u1 prime and u2 prime. And the assumption here is that, I forgot to put it here, but the assumption is that y1 is equal to e to the 2x and y2 is equal to e to the negative 2x. So we actually can imagine the differential equation, the homogeneous differential equation that we were solving, because it looks like R1 is equal to 2 and R2 is equal to negative 2, right? So it looks like our characteristic equation was R squared minus 4 equals 0. So the differential equation we're trying to square e to the 2x. So you can actually work backwards, right? And I'm getting this from my f, and I'm getting this from the roots, because I know that if your y1 and y2 look like this, then it must you had two real, right? So let's look at the system. So our system is going to be as follows. We know that y1 is equal to e to the 2x, and so if y1 is equal to e to the 2x, that means that y1 prime is 2 e to the 2x. And if y2 is e to the negative 2x, that means that y2 prime is negative 2 e to the negative 2x. So what I want to point out is that, notice that y1 prime is equal to 2y1, and y2 prime is equal to negative 2y2. Now, why is this true? Because what is y2? E to the negative 2x. So this part right here, e to the negative 2x, is just y2. So instead of keeping track of a whole bunch of, e to the 2x minus e to the 2x and all of that, we can rewrite our equation as follows. y1 prime y1 plus, u1 prime y1 plus u2 prime y2 equals 0. And then for the second equation, we'll have u1 prime. Now what is y1 prime? y1 prime is equal to 2y1. 2y1 plus u2 prime, and y2 is negative 2. So let's subtract. Minus 2y2 is equal to, now this x squared e to the 2x, we can write that as x squared y1. Okay, so this is our system. And now it looks like we can, let's see here, if we divide the second equation by 2, then we will have u1 prime y1 plus u2 prime y2 equals 0. u1 prime y1 minus u2 prime y2 equals x squared over 2 y1. The benefit of using y1 is that it clears up your notation, and it's easier kind of to see what's going on. Now I can just add both equations, add equation 1 to equation 2, and I get 2 u1 prime y1 is equal to x squared over 2 y1. Excuse me. So u1 prime y1 is equal to x squared over 4 y1. And I can bring this over, so I'll have u1 prime minus x squared over 4 times y1 is equal to 0. Now remember, y1 is an exponential function, right? Y1 is e to the 2x. So we know that y1 is never 0. And if the product of two things is equal to 0, remember, so AB equal to 0 implies A is equal to 0 or B is equal to 0. So if B is never equal to 0, then that means A has to be 0. So u1 prime has to be equal to x squared over 4, and u1 is just going to be the integral of x squared over 4 dx, which is going to be x cubed over 12. Okay? And once we know u1 prime, we can go back and figure out u2 prime, because u1 prime y1 plus u2 prime y2 equals 0. So if u1 prime is equal to x squared over 4, we'll have x squared y1 over 4 plus u prime y2. Okay, and so we can solve for u2. I'm being lazy. Let me copy, paste. So we're trying to solve for u2 prime. And we'll say that u2 prime y2 is equal to negative x squared y1 over 4. Remember, we know y1 and we know y2. So we're in good shape here. And now we just have to divide by y2. So we get u2 prime is equal to negative x squared y1 over 4 y2. Now go back. What is y1? Y1 is e to the 2x. What is y2? E to the negative 2x, right? But so now if I'm dividing by e to the negative 2x, that's the same as negative x squared e to the 4x over 4. Okay? And so, therefore, u2 is going to be the integral of negative x squared e to the 4x over 4 dx. And it looks like if we wanted to solve this, we would use integration by parts twice. Okay? All right. Thank you.